Assalamu alaikum. This is Project Fajr part number 4. We'll be talking about spectral fingerprints of Fajr. So based on this diagram, the different types of twilight, we have astronomical twilight, nautical twilight, and civil twilight. Our Fajr, it will be in between the civil and nautical twilight. So what is defined to be astronomical twilight by astronomers? So basically when the sun is below the horizon from minus 12 degrees to minus 18 degrees, it's called astronomical twilight. And then when the sun below the horizon again during sunrise, when the sun is below between minus 6 and minus 12, this is called nautical twilight. And when the sun is below between 0 and minus 6, we have what we call civil twilight. Anyway, we will be interested more on this intersection between nautical and civil twilight. This is what they call the blue hour. In this area where we will talk about what is the blue hour and how actually we can see it using a spectrometer, and what is that fingerprint or signature. So this is the blue hour. I'm not saying the blue hour is exactly Fajr. This is something that we have to determine based on the research we're going to be doing. So anyway, just remember those beautiful colors, golden, deep blue, then we have here purple, and then of course when it's astronomical, just like barely we can see light from the sun, and this is the astronomical twilight. So we move on and see how actually we can get our fingerprint and how actually the sun paints the sky. And based on this beautiful color of Fajr that we all know, we will see how we can actually determine Fajr, inshallah, not just by the photography, by the picture, when the sun is, when the sky is clear and there is no cloud, we can see beautiful sun. That's an easy, and we talked about this, we're going to be using a camera for that. But then when it's cloudy and when it's obstruction, we cannot see the sun. This is where we need to use the spectrometer, and we need to understand the radiation and how actually the wavelengths are behaving without looking at the actual image. So to understand that, I also want to show you basically some beautiful pictures. Here is nighttime, and since I couldn't just take a picture of night, it would be like really dark and you cannot see it. So I have a nice moonlight picture here. Here is the picture from scientists, what determine what is an astronomical twilight. And as you see, you can see the sunlight, but you barely see the background, like the trees and houses, and so we just see a little bit of light, but not much the outline, and only the outline of the urban area and trees and things like that. This picture basically shows nautical light, where there is more light, and with nautical, really, our eye basically made of retina, and retina has some sensors. And those sensors, they are more there's a red cone basically that depict the red color, and then there is a green cone so you can distinguish the green color, and then the blue cone, so we can distinguish the blue. And with all these with these three cones, we can make all kind of lights. But it's very, and as you see with the nautical twilight, there is a lot of purple here, and our eye, it would be very difficult unless if you have like really good eyes. I mean, it's not good eyes, but more like how sensible your cones to the violet. Anyway, here is another a picture or an image of what is the blue hour and how does it look. You can see it's this deep blue that you don't see during the day of the sky. And I will be talking why actually we see this deep blue when we analyze what's happening with the beam light coming from the sun going through our atmosphere and then finally hitting our eye, and then we can see this blue beautiful color here. Here is hopefully this is Al-Fajr, and based on so far depth research and talking to imams, and this is what Al-Fajr should look like. I might be still wrong on this, but this is also a part of our research to determine what is that image to determine Fajr. Okay. And here is the golden hour that we were talking in that picture. And the golden hour comes, it starts a little bit below 0 degree horizon. So it starts from the civil twilight and go maybe like 4 degrees above the horizon. So we have this beautiful golden color. And I'm going to come back to all this later on. I just want to show you some beautiful images. Okay, the sun, before it reaches Earth, it has to go through the atmosphere, and we need to know what makes this atmosphere. So, as you know, 78% of the elements or ingredients of the atmosphere is nitrogen. 21% is oxygen, and then you have only 0.9% of argon, and other gases represent basically 0.1%. So the nitrogen and oxygen is dominating this mass gas that basically make our atmosphere. So I'm just going to take an example of the oxygen, or basically the ozone, since it is the most abundant, well, not abundant in a sense, we have more of it, but in that ozone layer that basically the sun has to traverse, and we will see how this molecule basically, which is a trioxygen, impacts light going through the atmosphere in general, but going through the ozone layer. As you know, the atmosphere is made of not just from basically oxygen and nitrogen, but there is a lot of particles. There is vapor, there is droplet, there is dust. All these particles basically impact, and create some kind of obstruction to light. I'm taking an example of the ozone because of its impact on on this beautiful color that we see during Fajr. And I want to talk about the ozone, molecule, and also the ozone impacts color based on the wavelength. It would impact more the short wave, like the blue light, to the longer wave, like the red light. So let's take this example. So we have the sun. As you know, the sun, when you are above the atmosphere, it really will look like really white. As we are here on Earth, we see it as reddish, yellowish, but actually it's pure white. It's all the visible light mixed together. So we have the sun shining through the atmosphere, and in particular, this is the example we're taking here. That beam light hit, for example, a molecule of oxygen, and what happened after that? There are two phenomena. There is what they call scattering, and so that because of the size of the wavelength, which is smaller than the actual blue light, so that size, you will scatter basically the wavelength that's of blue lights. That's why we see the sky as blue. and it will impact less the other wavelengths, like red, for example, yellow, green. So it let them pass through, okay? And then we will have this phenomenon called scattering, using really Rayleigh, scattering. We don't need to get into like formula how Rayleigh is working, but basically there is a coefficient of 1 over lambda to the power 4, and lambda represents the wavelengths. So it will impact more shorter waves than longer waves. So if we have a person on Earth looking at the sun, so he will look at the sun, and then he's gonna see the sun more like orange, and the sky is blue because of this phenomenon that is there is a scattering. This molecule here, it basically scatters the blue, absorbs some energy, and let the other wavelength or light pass through. And so that's why we see this beautiful sun to be orange, and also the sky to be blue. So this is what's happening not just in the with the ozone molecule, but with nitrogen and other particles, like as I said, dust and pollen, and all these based on their sizes, and they will impact more certain wavelengths than the others. And we picked the ozone basically because of the impact of this blue light, and then you will let the and this is what we're going to need also to determine that beautiful orange color of the Fajr, inshallah. Okay, so I hope I didn't talk too much about this. I'm just going to give you this is just basically showing explain more actually what's happening with the sunlight. Here is our atmosphere made of multiple layers. I think there are like 5 layers. I'm just showing what's important to our project. This is the troposphere, basically that goes from Earth all the way to 10 kilometers, and this is called the troposphere here. This is where all the weather is happening and everything like that. The ozone, it is part of what we call a stratosphere. There is a thin layer there of ozone, and this is where actually this is very important layer. This is where, as I mentioned, where there is abundant amount of oxygen that make the ozone, and then we have oxygen there. So when I just want to basically explain this phenomenon and look at the elevation of the sun. So this is, I would say maybe in this scenario here, the sun is maybe like 5, let's say 8 degrees or 10 degrees above the horizon. Okay, so the sun beam traverse, as you see, less space inside the ozone, as if the sun is coming like really close or maybe tangent with Earth, like in this case here. Notice this this space here that was traversed by the sun. So when it traverses a larger distance, it will basically get into obstruction with the multiple atoms of ozone and other particles. So this distance here is very important during the Fajr, and I will show you more about this later on. So let's just take another example. For example, during midday, noontime, where the sun is on top of our head, notice this area here that the sun beam traverse. So it's very short, and there is not a lot of scattering happening here as to compare to if I go before, there's a lot of scattering here. So the sky is gonna, that's why that blue hour that I mentioned during Fajr, this distance is bigger, so there is more blue lights that is scattered. So we're gonna see like this deep blue, but also we'll see this beautiful orange. Okay. All right, so that's the idea about this ozone. That's what I was talking about. This is basically just showing you how this process of scattering. So when light hits the ozone molecule, basically there is a scattering here and absorption. So the blue will make the sky bluer, and of course we will see beautiful orange. And this basically it's a cycle. When there is a free atom of oxygen, you will find a molecule of oxygen and then make that ozone again. Okay, what we're really interested in is to find the fingerprint or signature. I called it fingerprint because basically it depends on each location. So it's really that fingerprint is based on that location where the sun and how dense the atmosphere with the ozone, and so that's why I give it a name fingerprint, but signature also that should be fine. But anyway, that's something that we can discuss later on. So this chart represents basically the absorption of the ozone of spectrum. Lucky the ozone basically take all the unhealthy ultraviolet that can burn our skin, take it out. This is how much absorption per centimeter square on each molecule. So like until maybe all this ultraviolet is being taken and not letting go through the ozone. So that's good for us. And just remember this this chart here. That absorption is done different based on which wavelength. Okay, but the main thing I want to show you here is this ultraviolet absorption that we will see it actually on the next graph. And I'm going to come back to this graph again. Okay, now we will see the twilight sky. The twilight, basically the band that we were talking about. Sky model. This is a model. We're going to see one scenario with the basically this is without the ozone. Means imagine all that light. We're measuring the light irradiance above the atmosphere. That's with everything else. Okay, so there is no absorption, there is no scattering, nothing else. This is the during twilight. This is the kind of spectrum we'll be getting. Now let's say this is without the ozone, means we are on above the ozone layer outside the atmosphere. Okay, now we are underground. I mean on Earth, and we are receiving that sunlight. So that blue basically depicts what is the spectral signature of twilight with the ozone. Means the sun has to travel the ozone layer, and this is what we get. Now I'm just gonna remember, we're gonna come back to this blue signature, and this is what we're gonna call fingerprint, and this is in general for twilight, and we're gonna develop it for Fajr, inshallah. Remember that the other picture, let me go back to it, or the other chart. So I took this graph here, this orange graph that represent the absorption of the spectrum, okay, for the ozone. Just remember this, and I'm gonna overlay it over this chart, and that's what you have here. Okay, it's outside because we started around 200, if I remember, nanometer all the way to 1200. That's why it's outside. But just remember, here when it picks, means it absorbs all ultraviolet. So all this spectrum here was absorbed by the ozone. That's why the spectrum we're getting on Earth is it's almost one irradiance here, okay? And then that's what that dip, it's very important. We're lucky actually we have the ozone that actually take all the ultraviolet and don't let it go through the atmosphere or the ozone, okay? Now this is basically the fingerprints that we were talking about, and this is by once we collect all the data we have on the Fajr, inshallah, and normalize it to one fingerprint, we should be getting something similar, where it's basically it peaked around 480 and then it drops down in this area. And reason why there's this drop, as I mentioned, there is a lot of blue that was taken away, and then we were only seeing, I mean, the ozone is not going to take all the blue. It will take some blue, and as I said, the ozone impacts all the wavelengths, but based on their, it would impact some colors more than others based on their wavelength, basically. Anyway, I just want to share with you this, and I thought, maybe we can have a discussion maybe this weekend or next weekend about what you think, and then I think this is a first step. At least we know what we're going to be looking at. This is some, I took a lot of scientist research and basically and documents and to come up with these things, and hopefully this is a first step to finding that fingerprints or signature of Fajr without looking at an actual image, just by looking at light. Thank you everyone, and probably I'll talk to you soon.